talked about accuracy and precision last year, and it's not a bad thing to review these two terms because they will pop up in the lab. Accuracy refers to having the right value. If there's a target you're trying to get at in the lab, we're trying to confirm the density of water to be 1.00 grams per milliliter. If you get 1.00 according to your lab data, you have accurate measurements, accurate data. Well done. So with accuracy, again, there's usually some kind of right answer that we're trying to confirm in the lab. Maybe we've done some stoichiometry and we know this reaction should produce 5 grams of copper. If we get 5 grams of copper, our data is accurate. Precision is a little bit different. We can look at precision one of two ways. One, it kind of deals with the measurement itself. Precision having to do with how detailed your measuring tool is, how detailed then your final measurement can be, the number of decimal spots recorded. So there could be a question that would say, like, which of the following is the most precise measuring tool? And we want to know, like, which one's going to give me the most detailed answer. In other words, which one would give me the most decimal spots? That'd be the most detailed or precise measurement. The other way we can look at precision has to do with a series of measurements. So they often show this example of like a dartboard, which is not bad. Let's say you run multiple trials. You're trying to confirm the density of water, 1.00 grams per milliliter. That's your target. Let's say I'm shooting darts, and the bullseye is my target. If I have something like this first picture, none of the shots are in the target. So the shots are not accurate. They did not get the right result, the desired result. And they're all over the place. Precision has to do with having reproducible data. You run multiple trials and you get the same results each time. That's precise data. This first one is neither accurate nor precise. So if I were running, let's say I have 3 trials. I'm trying to confirm the density of water. With my data, maybe I get like 1.55 grams per milliliter. I know that's not right, so I want to run it again. And I get like 0.68. Well, that's not right. I do it again. And this time I get like, I don't know, 2.07 or something like that. That's not good. If our target is 1 gram per milliliter, density of water, let's say that's what we're shooting for. Data like this would tell me that they made errors with each trial, and they probably made different errors. I don't know, one time they didn't zero the balance. One time they didn't measure properly on the graduated cylinder. One time they spilled half the water sample. And so if this were my conclusion, I was writing a lab report, I would say something about the specific errors in each trial. They must be different because I'm getting really different results. It's not reproducible and it's not accurate. The second set of shots is not accurate. I never got the bullseye, but it is precise. It is precise. Their results are reproducible. They shot in the same place each time. It just wasn't the right place if the bullseye is your target. Data like this might be something like, I don't know, 0.77 grams per milliliter, 0.79 grams per milliliter, 0.77 again, grams per milliliter. It was reproducible, it just wasn't correct. So again, now if you're writing your lab report and your conclusion, you're talking about your errors, data like this makes me think that they made the same mistake each time. So again, maybe each time they didn't have the proper mass. Oh, we forgot to zero the balance. Or maybe each time they didn't read their graduated cylinder properly. But they made the same mistake with every trial because their data is very similar, very reproducible. It's precise. Finally, we get the right target here. So this last one is both accurate and precise. So this is good results. Maybe it's like 1.02 grams per milliliter, 0.99 grams per milliliter. Oh, and what the heck, the last time they got it perfect, 1.00 grams per milliliter. Well done. These are the kind of conclusions you love to write because you didn't have a lot of errors. So say, we made proper measurements with both the electronic balance for mass, the graduated cylinder for volume, and each time our data was not only accurate, but in the end it's very precise, it's very reproducible. So again, the accuracy thing is probably going to come up if we're shooting for a specific target, a specific mass, a specific volume, a specific density that we're trying to confirm in the lab. Precision will come into play if we run multiple trials. And so again, here's a set of data. This could be like a good multiple choice kind of question. Whose data is most accurate? Whose data is most precise? If the correct measurement was supposed to be 4.560 grams. Okay, so the accurate part, who's closest to 4.56 grams? Who got the closest data? Let's see, what do we got here? How about student 1? That's all pretty darn good, isn't it? But especially this guy. It's perfect. Trial 4, student 1. Perfect data. They hit the target. Finally, trial 4 is accurate. Whose data is the most precise means who got like the most reproducible results. Student 1 is still pretty good data. I mean, they're all in the ballpark. Student 2. Whoa, student 2 is all over the place. They've got issues. They'll probably blame their lab partner or something like that. Student 2, no. 4 grams, 6 grams, 3 grams, 5 grams, they're everywhere. Student 3, 6.172, 173. Ooh, this looks good. Okay, well, I should take that back. This is not accurate, but it's very precise. It's almost the exact mass every single time. It's just not the right mass. Student 4, they're all kind of around 4 grams, 4.57, 5.4, 5.7, 5.6. I think I'm going to give this one most precise. I think I'm going to say student 3. It's not accurate. So they probably made some kind of an error, but they made the same error every trial. But it's very reproducible. They almost got the exact same number every time. So again, something to think about when you have data where you ran multiple trials. Something to think about writing in your conclusion. And finally, the other thing I want to look at in terms of this precision element to making a measurement is the detail of your measuring tool. So precision can refer to having reproducible data. It can also refer to having detailed measurements, and that's all dependent on the measuring tool you're using. Which of the following measuring tools could make the most precise measurement of 75 milliliters? This just kind of goes to good lab skills. When you are measuring volume, the objects that you probably have available to you are graduated cylinders in different sizes. We usually have like a 10 milliliter and a 100 milliliter. Beakers. Beakers we have, again, varying sizes. There's usually like a 100, a 250, maybe a 400. And flasks. Now there are a few different kinds of flasks. This flask shown here is called a volumetric flask. You may or may not have used a volumetric flask. They kind of got this like really skinny neck, and they usually have some kind of a cap on top. Volumetric flasks are used for making solutions. Volumetric flasks for making solutions. They're not used for making measurements. Because here's what happens. This is a 250 milliliter volumetric flask. You can't really see it too good on this picture, but these volumetrics usually have one line on them. And then it would say like right here, 250. You would only use this volumetric flask if you wanted to make 250 milliliters of solution. That is the only marking that'll be on this thing. Now these are nice for making solutions because again you can like put the cap on them and then you can really like swirl them good and it's not going to fly everywhere. You're going to make a nice solution. But in this case there is no mark for 75. Would 75 milliliters fit in this measuring tool? Absolutely. But I have no clue where that would be. Volumetric flasks are only used for making specific volumes of solutions. So we're not really going to use these in the lab. Now the other kind of flask that we should mention, you will have available to you. Yeah, it's a little exaggerated, but it's not too bad. Do you remember these guys? These are in your drawers. These are called Erlenmeyer flasks. Erlenmeyer flasks, you'll use these all the time. You'll use these like when you're, maybe you're doing some stoichiometry and you want a filter. We might use these if we're titrating. They're in your drawers, they're great. They have markings on them. Similar to markings on a beaker, they're usually marked either every 25 or every 50 milliliters. So there might be markings, something kind of like that. So this could be like a 250 milliliter flask. We've got those in the drawers. The problem with the flask and the beaker, again, markings very similar. Usually either every 20 or 50 milliliters. And it's kind of hard to see again on this picture here, but I think this is at like 50. So there's kind of a line here for 50, and this would be 100, 150. This is like 200, and this is like 250. And the flask would be very similar. Would 75 milliliters fit in the beaker and the flask? Yeah, absolutely. Well, on this beaker, like you could estimate, you could tell it's somewhere halfway between the 50 and the 100, but is that really making a proper measurement? There is no line for 75 milliliters on either the flask or the beaker, unless it has like a 25 milliliter mark, but these usually don't. The beaker and the flask are great if it said, hey, get approximately 75 milliliters, or sometimes they might need approximately 100 milliliters of water. Excellent, use the beaker, use the flask. Often we do reactions in beakers and flasks. We can get in there and we can stir really well. But they're not a good choice if you need to make a very specific measurement. In that case, the winner is our buddy, the graduated cylinder. Graduated cylinder is always the best for making your initial measurement. There is a line for 75 milliliters. There she is, 75 milliliters. And then I would put like 75.0, 75.00, depending on the markings of my graduated cylinder. That's the only one listed here that has a line for 75. Now I would pour that 75 milliliters of solution into a beaker or a flask when I'm ready to do the reaction. This always drives me bonkers. It's kind of off the path a little bit. People will do reactions in a graduated cylinder, and then they'll be like, my stirring rod doesn't hit the bottom, like I can't stir this good. Yeah, graduated cylinders are for measuring. They're not good for like doing a reaction where you got to mix things and make observations. No, that's not a good idea. You'd want to do the reaction in the beaker or the flask, but make the measurement in the graduated cylinder.